We have seen that when a ball moves from here to here along a circle, we can find the change in direction by subtracting the two velocity vectors using this triangle law for subtracting vectors. And so this gives us the change in velocity as this vector. And according to Newton's second law, the force must be in the same direction as the change in velocity. Okay. So that means that the force must be somewhere around this direction. Now what I like to do now, alright, is this. That the force in this direction is like an average direction of the force that acted over this period as the ball moves from there to there. But what I would like to do now is to find the instantaneous force. That means the actual force that is acting on the ball at a particular instant in time, or if you like, over each extremely short interval of time. And in order to do that, what I'm going to do is I'm going back to this look at this picture here, and instead of looking at this case where the ball has moved from there to there over an angle of pi over 3 radians or 60 degrees, I'm going to imagine that the ball has only moved for a very short time or over a very small angle. So let's draw that. Now, so I'm back to the starting position of the ball, and what I'm going to do now is this. I'm going to imagine that the ball has only moved for a very short time. So there's a very small angle there. Okay. Now let's say that it has moved for a time of maybe 0.001 of a second. Okay. Very short time. Now, and suppose that the radius of this circle is 2 meters. 2 meters. So what I want to do now is to find the change in velocity. Alright, I want to know both the magnitude of this change and its direction. So how can I do that? So think about the new position of the ball. Okay, at the old position, the starting position, the ball has a velocity in this direction. But after moving for a short time, the angle is slightly tilted. So I have a new velocity in a slightly different direction. Okay. So the tail of the vector was here at first. It has now moved a little bit to there. Alright. Now using the previous way, I can find the difference between the vector by drawing that triangle. So I start by moving one vector to here. So that's my first vector, which points vertically. Okay. Then my other vector is there, which is slightly tilted, but it still has the same magnitude, meaning the same length. So I must move that, keeping its direction unchanged until its tail touches the tail of this vector. like this. So that's my final vector, my initial vector, my final vector. And using this subtraction law for vectors, the change, right, the difference between these two vectors is the arrow joining one tip, the first tip to the final tip. It's this arrow here. Let me try and draw it more closely. So, right, the arrow is this arrow. Okay, something like that. Now let's think about trying to find the direction, okay, and the magnitude of this error, so we know what the change in velocity is. The more obvious thing is the direction. So I talk about that. Now, if you look at this, triangle, once again we have isosceles triangle. This side is equal to this side. If you look at this is a very small angle. Okay, we'll work that out in a moment. This is a very small angle, and if you look at this change, this line here, this little arrow that represents the change in velocity, clearly it looks very much or very close to 90 degrees relative to this starting velocity. So this angle here is very nearly 90 degrees. And you can imagine that the smaller this angle gets, I call that theta, which is the theta here. The smaller this angle gets, the closer the more horizontal this is going to be, if that's vertical. The closer this and this line would be to 90 degrees. So in other words, the change in velocity, okay, is at right angles. It's the instantaneous change, all right, over extremely short time. This change in velocity is at right angles to the starting velocity. And since we know that the change in velocity is in the same direction as the force, that must mean that when the ball moves by a little bit, okay, since the change in velocity is perpendicular to its motion, the force causing this slight change in direction has to be at right angles to the velocity. Okay, now there's one condition here, must not forget. The condition is that this final velocity has the same magnitude. So in other words, it's a uniform motion. Okay, there's no acceleration along the direction of velocity. The speed remains the same. So in a case where the speed of this circular motion remains the same, therefore, we have just found quite clearly that the force must be perpendicular to the velocity. So let me write down these important results. Right, for a uniform circular motion. Okay, the word uniform means that the speed is the same around the circle. We have now seen that the force is perpendicular. I'll use that symbol to mean perpendicular to the velocity. Okay, so that is a right angle. That is a right angle there. Okay. Now, and another way to look at this, is that if the force is perpendicular to the velocity, then from this picture, clearly the force is pointing right at the center. So the force points exactly at the center. Okay, and this is our centripetal force that I've described previously. That's called a centripetal force. And this is a very important result, okay, about motion in a circle.